Hello again. Today we move to our next topic on digital design course, secondary logic gates. In the previous lecture, we got familiar with the basic logic operations and gates and or not, and or not. We can implement any logic functions using the basic logic operations and can implement the logic circuit using the basic logic gates. But there are secondary operations and gates that are useful. Buffer, NAND, which is not and, NOR, not or, exclusive or, XNOR, inverted and inverted or. Now we'll look in detail on this function. First, buffer. The graphic symbol for the buffer, X, and on the output we have the same input, X. This gate is useful sometimes for delay and other purposes. Next, the NAND, which is really and followed by a not. We have X, Y. Here we have X and Y, and X and Y all not. And the graphic symbol for the NAND is like that. Here, X, Y, X and Y all not. All not. This is the NAND operation. And we can, for the NAND, obtain the truth table. We have two inputs, so we list the states, X and Y, 0, 0, 0, 1. And for the NAND, X and Y all not, which is 1, 1, 1, 0. This is the NAND operation. Next, we move to NOR. NOR, which is not or followed by X, Y. So here we have X or Y, and here X or Y, all not. The graphic symbol for the NOR gate, XY, X or Y, all not. And again, the truth table for the NOR, 0, 0, 0, 1, 1, 0, 1, 1. Here, X or Y equals to 0, 1, 1, 1. And the NOR, X or Y, all not, which is 1, 0, 0, 0. These two gates, NAND and NOR, are very useful since we can implement any Boolean function using only NAND gates or using only NOR gates. And we will prove that, and I will show you how to implement any Boolean function using only these gates. So these gates are called universal logic, any of them gates. And any logic circuit can be redrawn using only NAND gates or using only NOR gates. Next, we move to the next secondary logic operation and gate, XOR, exclusive OR. By definition, we have two variables, 0, 1, 1, 0, 1, 1, X exclusive OR Y, this is the symbol used for the exclusive OR operation, is equals to 1 if the variables are different. So here and here. And if they are equal, the function equals to 0. The graphic symbol for the XOR, XY, X exclusive OR Y. From the truth table, you can derive the function by means of inputs. X exclusive OR Y is equals to 1. In this case, when X is equals to 0 and Y 1, so we write not XY, or when X equals to 1 and Y equals to 0. This function cannot be simplified anymore, so it's a minimal form function. The exclusive OR gate is very useful, and we will use it in the design of several logic circuits. Next, the complement of this function is the XNOR. XNOR. By definition, the XNOR, I will write it the complement, but there is another symbol used, X equivalence or Y, like that. X exclusive NOR Y is equals to 1 if the variables are the same, and equals to 0 otherwise. And the graphic symbol XY for the exclusive NOR is like that. X equivalence or Y or exclusive NOR. We can obtain the function from the truth table. It's 1 when not X, as you see, not Y, or when X, Y. Again, you cannot simplify this function anymore. It's in the minimal form, and the XNOR again is a very useful gate. We will use it in the design of several logic circuits. Regarding the exclusive OR, it's equal Y exclusive OR X, and it's very easy to prove that, since the left side is equals to X not Y or not XY, and the right side equals Y not X or not YX. So they are the same. And X exclusive or y together exclusive or z is equals to, we can x exclusive or y altogether exclusive or z. You can open the left side and the right side. I'll write the first steps for you. X ANDed with y exclusive or z or not, or not x ANDed with y exclusive or z. And this is x, y not z, or not y, z or not, or not x, again ANDed with y not z, or not yz. This one, the complement of this one is again y not z or not, ANDed with not yz or not, or the same term y not z or not yz equals to here again you can use De Morgan law, x not y or z ANDed with y or not z. Do you see I could write it from here, the complement we replace the and by or, the or by and we complement the variables, or not x ANDed with the y not z or not y z equals to, here y and not y 0 with, so not y not z, x not y not z, or x y z, z y with x, z or not z 0, so we do not need to write here not x y not z, or not x not y z. So this is the left part, and now the right part I will write it's equals x or y ANDed with not z, or x exclusive or y, all not ANDed with z. And I think it's easy for you to continue. You will receive the same expression, which means that exclusive or rule is valid. We move to inverted AND gate. Do you see in the inverted AND, you invert the variables before ANDing them. Here x, y, then the output is not x and not y. And the truth table for the inverted AND gate, so yeah, not x is 1, 1, 0, 0, not y is 1, 0, 1, 0, and now we AND these terms together, not x and not y. 1, 0, 0, 0. We already know that this is the NOR. So inverted AND is equivalent to the NOR here, X or Y or not. And you can see by using De Morgan's theorem that these are the same. Next, the inverted OR you have to complement the variables before ORing them. So we have not X or not Y. And again, the truth table is easy to obtain. Here, not X 1100 and not Y is 1010. Now you have to OR these two terms 1110. And again, you are familiar with this form, it's a NAND. So inverted OR and NAND X, Y, and here we have X and Y or not are equivalent. And you can see the algebraic form for each of them, they are the same. These are the most common used secondary logic gates. So now we have the basic logic operations and gates, and or not, and or not, and the secondary logic operations and gates. They are buffer, NAND, NOR, exclusive OR, exclusive NOR, inverted and inverted OR. For now, thank you.